Hi, I hope you're having a great day and welcome to today's topic of resistors. What are they and what do all the markings mean? And how do they work? To understand all of that, I'll first need to explain resistance. Now, what is resistance? Well, resistance is often defined as the ratio of potential difference across a conductor to the current flowing through it. So from that we can achieve this equation. R represents the resistance in ohms, V is the potential difference across the conductor represented in voltage, and I is the current that is flowing through the conductor and its units are ampere, A for ampere. Now if you have difficulty memorizing this equation, R equals to V over I, there's a few ways that you can memorize it. One way is using the triangle method, where V is on top, I and R are at the bottom. So to explain how to use this triangle, I will go step by step. So the horizontal line here represents division. The vertical line here represents multiplication. So let's say if you're required to find the value of V. So V is equal to I multiplied by R. If you're required to find the value of I is equal to V divided by R. And for R, we will apply the same method. R is equal to V divided by I. So that's for the triangle method. The second method is the algebraic method, where you just memorize this equation V equals to IR, and to find the values of each of these variables, all you need to do is make each of these variables the subject of the equation via algebraic manipulation. So if you want to find the value of I, you just make I the subject, you get V over R. If you want to find the value of R, you get V over I. As simple as that. Now, current is often defined as the rate of flow of electric charge through a given cross-section of a conductor, right? So dq dt just means the amount of charge that is flowing through a period of time. So conventional current is said to flow from the positive terminal of the battery to the negative terminal of the battery, right? So it would flow this way and come back here. But what's really happening is that electrons are flowing out from the negative terminal, right? This is the flow of electrons that are flowing out of the negative terminal and into the positive terminal of the battery. Confusing, isn't it? Well, to explain what's happening here, I need to emphasize that frame of reference is a very key concept when we are learning physics, and it comes into play in this exact scenario over here. Let's take a metallic wire of a circuit, for example. The positive metal ions are fixed in a giant ionic lattice structure. While there are a sea of delocalized mobile electrons that are moving in between these fixed positive ions. If the electrons are moving to the right, taking this movement as the frame of reference, the positive ions are technically moving to the left. Although in reality they are held in fixed positions. This relative flow This relative flow of positive ions is then taken to be the conventional current I. Potential difference is the amount of electrical energy converted to other forms of energy when a unit charge passes from one point to another in a circuit. In this equation, potential difference V, which is measured in volts, is equivalent to the energy in joules in the energy converted per unit charge coulomb that passes from one point to another in a circuit. So now that I have explained how current works and what potential difference is, let's take a look at a visual to better understand how resistor works. Let's say we have a pipe that is flowing through a box and is connected to a pipe that is enabling the water to flow out of the box. So there's water flowing in and there's water flowing out. Let's say this box is completely empty and that the water is flowing into the box at 1 liter per second and is flowing out of the box 1 liter per second because there is no resistance in the box that is blocking the flow of water. Now, if I were to add some stones in this box, all of a sudden the water would now exit the box at a slower rate because now there is a greater friction due to the blockage caused by the stones in the box. Hence, the water particles lose kinetic energy and thus its speed reduces and it would output at a rate that is much smaller than 1 liter per second. These stones represent the atoms of the resistive material used in a resistor. Now, there are a few ways that we can increase the resistance. One way is that we can make the box much longer while keeping the cross-sectional area of the box the same. A longer box would mean that the water would have to travel and thread through a greater number of obstacles, leading to a greater loss of kinetic energy, leading to a slower speed. Hence, the water would output at a rate that is much lower than 1 liter per second. Another way is that we could decrease the cross-sectional area of the box while keeping the length of the box the same. Essentially, we are making the box thinner. Hence, there will be lesser space and gaps for the water to pass through. When the water comes from a bigger cross-sectional area and collides into a smaller cross-sectional area with obstacles, once again there is a reduction in speed due to resistance against the flow of the water. These two factors, together with a constant, can then make up an equation to find out the electrical resistance of a conductor, wire, or any circuit component with a resistance. The equation that we're going to learn is this. R equals to rho L over A. Rho represents the resistivity of the material used and it is measured in ohm meters. L represents the length of the object that the current needs to travel through, measured in meters. A is the cross-sectional area of the object and is measured in meters square. And R is the resistance of the object, measured in ohms. By making rho the subject of the equation, we can see that rho equals to Ra divided by L. So R having the units of ohms A having the units of meter square, L having the units of meter, we can now see that this cancels out with this, and therefore the units of rho is ohm meter. Now I must inform you that the resistance of a resistor is not constant. Even if it's a certain material of a fixed length and area, it steadily increases as temperature increases. Now you may be wondering, why is this the case? Because the hotter the material, the hotter the material, the more its atoms or ions vibrate, and there is an increase in the average number of interactions of the atoms or ions with the electrons. Thus, the harder it is for the electrons to wiggle through, which translates into higher electrical resistance. Besides a few exceptions, broadly speaking, the resistivity of most materials increases as linear temperature increases. So if you increase the temperature by 10 degrees, the resistivity would also increase by a certain amount. If you increase it by another 10 degrees, the resistivity would also increase by the same amount again. Alright, so now that we know what resistance is and how it works, let's talk about resistors. People who make electric or electronic circuits to do particular jobs often need to introduce precise amounts of resistance. They can do that by adding these tiny components called resistors. A resistor is a little package of resistance. Wire it into a circuit and we reduce the current by a precise amount. From the outside, the resistors all look more or less the same. As you can see in this drawing, the resistor looks like a worm-like component with colored stripes on the side. It has two connections over here and here, so you can hook it into a circuit. Now for circuit diagrams, the symbols of resistors are often pictured in this manner, or they can also be drawn in this manner. Both represents the same thing. Both means that there is a resistor that is in the position of this symbol. Now if you break open one, you might see an insulating ceramic rod running through the middle with copper wire that is wrapped around the outside. A resistor like this is described as wire wound. The number of copper turns controls the resistance very precisely. The greater the number of copper turns and the thinner the copper is, the higher the resistance. In smaller value resistors designed for lower power circuits, the copper winding is replaced by a spiral pattern of carbon. Resistors like these are much cheaper to make and are called carbon film. Generally, wire-wound resistors are more precise and more stable at higher operating temperatures. The color codes on these resistors have a meaning to them, and they enable users and manufacturers to read the resistance and tolerance that a resistor offers. The number of color bands may vary depending on how it is manufactured. Some only have 3 bands, some may have 4 bands, and some may even have 5 bands or 6 bands. No matter how many bands they may have, they all follow the same color code. Usually these stripes will be flushed together to one side of the resistor. If not, you can also look for the gold or silver stripe, which will represent the last stripe of the resistor. Sometimes resistors don't even have any gold or silver stripe at all. Here is a reference chart for the color codes for the bands of resistor. I will give some examples. You can pause the video at any time to refer back to this point and then figure out the resistance of the resistors in the example on your own before I give you the answer. I will label the color of the bands in case some of you guys are colorblind, and it should help you to follow along and learn too. Here we go. Now let's take a 4-banded resistor as an example. Brown, black, red and gold. These are the lines that are drawn on the resistor. So the bands that are drawn on the resistor here will represent the numbers 1, 0 and 2. Let's just ignore this 4th band over here for now. The first 2 stripes represent the first 2 digits of the number. So the number will start off with 1 and then 0. And then the 3rd stripe here is called the multiplier. You can think of it as the number of zeros that can be added to the end of the number. So basically it will be 10 to the power of 2 multiplied. So in this case, the resistance would be 1000 ohms or 1 kilo ohms. Both are of the same value. Now let's take a look at a 3-banded resistor. Here we have brown, black and orange stripes. You can pause the video here to figure out the resistance. Alright, have you figured it out? So looking at these stripes, the numbers would be 1, 0 and 3. So this would mean that the resistance here would be 1, 0 times 10 to the power of 3, which would give you 10,000 ohms or 10 kilo ohms. If you got this answer, well, congrats, you did well. If you didn't, do not worry, there's always another chance to try again. Here's another one. Yellow, purple and red. Pause the video and give it a try. Alright, so the numbers here will represent 4, 7 and 2. This means that the first 2 digits would be 4 followed by 7 and then multiplied by 2, or you can think of it as 4, 7 followed by 2 zeros, which would be 4,700 ohms or 4.7 kilo ohms. This next one has brown, black and green stripes. Pause the video and give it a try. Now this resistor has a very large resistance. It actually has a resistance of 1 million ohms or 1 mega ohms. This next one here will be a tricky one, so please be careful. The resistor has the colors brown, black and black. If we follow the color code, the numbers here will be 1, 0 and 0, which would mean that the first two digits are 1 followed by 0 and followed by 0 zeros. So it will be 10 to the power of 0, which will just give you 10 ohms. Therefore, this resistor here has a resistance of 10 ohms. Now, let's go back to the 4-banded resistor. You may be wondering, what is the purpose of this last fourth band over here? The fourth band here could either be gold or silver. The gold represents 5% and the silver represents 10%. Now, everything in electronics doesn't always have an exact whole number for its resistance. There will always be a margin of error due to our limitations of how accurate the resistance will be while manufacturing it. A 10 ohms resistor may actually be 9.75 ohms. If there is a gold band, it means that there is a tolerance of 5% within its specification. If there is a silver band, it means that there is a tolerance of 10%. So if a resistance is specified to be 1 kilo ohms and it has a gold band, it means that there is a plus or minus of 5% or 50 ohms, because 5% of 1000 ohms is about 50 ohms. So that would mean that this resistor here has a resistance of somewhere between 950 ohms to 1050 ohms. For a silver band, it would be a plus minus of 100 ohms. So that would mean that this resistor, if it were to have a silver band as the tolerance band, would have a resistance of between 900 and 1100 ohms. Now, if there is no tolerance band at all, like a 3-banded resistor here, that would mean that it has a standard tolerance of 20%. So no band, no tolerance band would mean 20% tolerance. Now, if you encounter a 5-banded resistor, they are usually known as precision resistors, and they often end with a brown stripe, denoting that the resistor has a tolerance of 1%. Therefore, it is known as a precision resistor. So let's figure out the resistance of this resistor right here. It has the colors blue, black, orange, and brown. So this would mean that the numbers here are 6, 8, 0, and 3. So hence, the first three numbers or the first three bands represent the first three digits, which are 680 multiplied by the fourth band, which is the multiplier band here, is 10 to the power 3, and it will give you 680,000 ohms or 680 kilo ohms. Here's another example. The colors here are blue, gray, black, black, and brown. Pause the video here and give it a try. All done? Let's get to it. So the numbers here would be 680 multiplied by 0 zeros. The fifth band here, remember, it is just a tolerance band, which represents that it has a tolerance of 1%. So the resistance of this resistor would actually be 680 times 10 to the power 0, which would give you 680 ohms. Now with that, I hope you have a better understanding of how a resistor works and how it contributes to a circuit, and what the markings mean, and how a person is able to read the markings and figure out the resistance of the resistors. With that, thank you for watching. I hope you learned something and have a great day. Bye.